Okay, so over the next few days, I think we really just have 3 days, today and then next Tuesday and Thursday before the AP test. What I'm going to do, I just went through the last 2 years and I pulled out the questions that are pretty much on there every single year. I don't know what that first question is going to be. Could be really anything. There's a lot of common questions that they're going to do. You're going to see 4 of them here that pretty much year in and year out, you're going to get some type of question on that. So I've gone through the last 2 years, 2019, 2018. I pulled out 4 that you're always going to do. With that being said, the ones that I'm not going to do, because I've largely done this already, is this 9.3 day number 3. We did this before our test that you guys would have just taken on Chapter 9. These were all old free response questions on the Taylor series, on L'Hopital's rule, approximating values using a Taylor series, Taylor polynomial. So this absolutely should be something that you know very well. You would be doing yourself a disservice if you can't look at these and understand these pretty well before you go into that test. So I would definitely have that packet available to you. Look that over, make sure we're all squared away, make sure we can do the work that was in 9.3 day number 3. Okay, so hopefully you've done that already. You've got them in front of you. Definitely look those over. Today I'm not going to do any of these series questions. We just spent the last few weeks doing them, and then you've got 9.3 day 3 with a bunch of them on there already. We are going to focus on the other types of questions that are also pretty common to what they put on there almost every single year. Okay, so the first question, it says, this is number 1 from last year, so very relevant, nothing old. And again, for the last pretty much 19 years, this type of question is on the test. Fish enter a lake at a rate modeled by the function e. So we talked about when we did this, the idea of rate. When they use that word, you want to understand what that means. And then they give you that function. So e of t is the rate that fish are entering the lake. The fish are leaving the lake at another rate. So the rate they leave is given by this function. Both e of t and L of t are measured in. And then if you didn't pick up on the word rate, when they give you this word, this unit here, fish per hour, what that is telling us we're really dealing with, if you think in terms of position, velocity, acceleration, we're dealing with a velocity, fish per hour. And then t is measured in hours since midnight, the time of 0. We have done these in school. We did a bunch of these, and that's because you see them every year. So this hopefully we remember. So letter A is asking how many fish, so that's what we want to end up with, enter the lake over the 5-hour period from midnight t equals 0 to 5 a.m. Then give your answer to the nearest whole number. So pay particular attention to this. You don't want to give away free points. The rule is 3 decimals unless they specify differently, which clearly they do right here. So if we are currently at fish per year, so if we come back up here, that's what E of t and L of t are measured in. We ultimately want to get to a unit of fish. We are going to be going from our velocity to our position, and we are doing that with the entering rate. So the way we go up is through integration. Integration accumulates change. So what we would set up, I'm going to squeeze this one in here because it's short and sweet for part A, is we would need to integrate over the interval of 0 to 5 the function e of t times dt. E of t, this function had units of fish per hour. We're multiplying that by a 5-hour period. So fish per hour multiplied by hours should leave us with a unit of fish. You don't have to label them. They don't ask you to label this. I would discourage you from labeling it just in case you label it incorrectly. This would be on the calculator for this one. They're telling us we don't need a calculator for this. So it would be something that you would be able to handle by hand possibly. If you have the calculator in your handle, they did say you can go ahead and throw that in, even if it's a simple one. All right, so we would take that, we would throw that into our calculator. And when we do that, we should get 153.458 fish. And then I just almost broke my own rule here. They said round that answer to the nearest whole number. So we would end up with 153 fish. B, they ask you for the average number of fish that leave the lake per hour over the 5-hour period from midnight, again from midnight to 5 a.m., 0 to 5. So similar, we want to figure out the average number. So there's really two averages that we've dealt with: average rate of change, and we've dealt with the average value. With all these problems, we really want to understand what units are we at, what units do we ultimately want to end up in. So since this should be the average number of fish that leave per hour, our unit for letter B should be fish per hour. If we do this, we are effectively taking the derivative of our velocity, and what that would give us is an acceleration unit, fish per hour squared. We don't want that. So this is not an average rate of change question. This is an average value question. So what we would set up is 1 over b minus a, which we know. 5 minus is 0. We would then be doing the integral from 0 to 5. Since we are now talking about leaving the lake, we would call that L of t times dt. Think about what unit that integral would produce. We just did it in part A. When I integrate our rate, we're going to end up with a unit of fish. So when we do this part of it, the integral of L of t from 0 to 5, that will give us a unit of fish, but then we're going to turn right back, take this fraction, the 1/5. Know what that denominator stands for. 5 minus 0 is hours, so what that would leave you with is fish initially when we do the integral. But when we then multiply that by the 1 over 5, really the 5 in our denominator is a unit of hours. That will give us the proper unit of fish per hour. Becomes calculator at this point. We would throw that into our calculator. Should get 6.059 fish per hour are leaving the lake. C, at what time in the interval of 0 to 8 is the greatest number of fish in the lake? They want us to justify our answer. So this is a big one. This is very, very common. All of this is. We've done a bunch of these. It has been a while. But remember how we're talking about basically a maximum number of fish. We have a closed interval. They want us to justify. There's a few routes we could take. The easiest way to justify this, I'm going to do this one down here because we're going to need a little bit of space, is to list your candidates. The two candidates that are simple, since we have a closed interval here, are the time of 0 and 8, the two endpoints. All right. We probably have another time that we need to figure out. That would be, again, if we want the maximum amount of fish, we would want to know what's the equation for the amount of fish at any time. If we can write that equation, it would then be when the derivative of the amount of fish is either equal to 0 or is undefined. A and B, we've kind of alluded to how we can find the amount of fish at any particular time. You were not told that there were any fish in the lake initially. So the way that we can calculate the number of fish is by integrating from 0 to any time that e function. If you remember, we want to call this a different variable now. So e of x is how fast the fish are going into the lake. The L function is telling us how quickly they are leaving the rate. So that is the equation that would give us the amount of fish in the lake at any time that we would like. If we took the derivative of this, we are then taking the derivative of this integral. Those would cancel, and the t would just get substituted in. So a prime is equal to e of t minus L of t. Again, you're not supposed to have to use your calculator. This would be something that if we had this in a couple of weeks, you would be able to do on your own by solving this algebraically. For what we're doing right now, when we take these and set them equal to 0, you would be graphing them on your calculator and then calculating the 0. When this would have been done, you would have gotten 1 and only 1 0 for this. And you get 0.20356. That is our other candidate. With those being our three candidates, the easiest way now to go about this is to do this. What is the amount of fish at 0? What is the amount of fish at 8? And then how many fish do we have at the 6.20356 time that we had here? Okay. You would then come back up to this original equation. This equation here tells us how we can figure out the amount of fish at any time that we want. First one is pretty simple. A of 0 is going to be a 0, so that obviously is not going to be your answer. But then we would take 8, plug it into this equation, take that 6.20356, plug it into this equation. Whatever those give us, the biggest one has to be our answer. Okay, so sorry. When this is a PDF, I can't erase very well. It's a pain in the butt. So I'm writing small here. At 8, when we plug that in, you can plug it in if you'd like. Promise that's what you're going to get. 80.9899. That's how many fish we have at 8. And then plug this one into your calculator. Let's see if I can move this a little bit. So the amount at that 6.20356 would be 135.015. That is your justification. If you have all of this, you've justified your answer. Justify it means you don't necessarily have to put it into words. When we get down here to D, when they say explain, then you're going to have to use words. So this is our justification. This is the time and when we have the most number of fish in the lake. All right. And then D, sometimes you can get a little lost in the word rate. What's rate mean? What are we finding the rate of? D is asking us find the rate of change. So pretty much our derivative or average rate of change, one or the other. How quickly is the rate changing in the number of fish in the lake increasing or decreasing? So is the rate of change in the number of fish in the lake increasing or decreasing, and then explain your answer. So think about our equations. A of t is the integral from 0 to t for the entering rate and our decreasing rate. So this has a unit of fish. So if we took the derivative of that, that would give us the rate of change in the number of fish in our lake. What B is asking you is the rate of change. Rate of change is basically the derivative. So take the derivative of this, which we've already done up at the top. It's E of t minus L of t. They're asking you if the rate of change, this guy right here, is that rate of change in the number of fish in the lake, is that increasing or decreasing? It's not asking if the number of fish in the lake is increasing or decreasing. It is asking you if the rate of change in the number of fish in the lake is increasing or decreasing. So what it's really asking you is A prime increasing or decreasing? Well, we can determine if anything is increasing or decreasing by taking its derivative. So we would want the derivative of A primed, which would then be E primed of t minus L primed of t, and we want to evaluate it at the time you were given, which was 5. This would have been a Math 8 button. You know, you'd have to use your Math 8 option. That's how we do derivatives on the calculator. Again, without having to be forced to use your calculator on this exam, this would play out where you should hopefully be able to do this without a calculator. But we would then have to just plug in what's our E derivatives value at 5, subtract that by the derivative value of L at 5, and then whatever that gives us based upon the sign would tell us what our answer is. That would have given us a negative 10.723. Since that is less than 0, the rate of A prime is decreasing. All right. So that's problem number 1 in terms of questions and almost are always on there. Next one. We did a bunch of these also back in the day. And again, we did a bunch because it's almost always on there. So this is our derivative graph. So you're given a graph of f. So understand that first and foremost. It tells you this is a continuous function f. It's defined on the closed interval from a -6 to 5. The figure above shows a portion of it. What that basically is just alluding to, we're supposed to be defined from a -6 to 5. We have 5 up here, but notice how we only start at a -2. So they're only going to show you a portion of the graph. Like I said, they're going to find different ways to ask these questions. Every year there's a little bit of a tweak. Don't freak out. Just focus on what we know and then apply it. And in this case, last year they basically just removed part of the graph. First time they've ever done that. Who knows what they're going to do for you guys. You just got to be prepared. So they take a portion of that graph. They're going to show it. They take a portion that you can't see as well. It consists of 2 line segments and then a quarter circle that's centered at 5, 3. So this point right here is the center of a quarter circle. They're obviously giving us that for a reason. It is also known that the point 3, 3 minus root 5 is on that graph of f. This is the graph of f. So they're telling you, since this is not a nice value here, that we can just look at the graph and determine, they're giving you that value. They're telling you that it is this point. Letter A. They then tell you that if we were to integrate from a -6 to 5, you're going to get a value of 7. We have to trust them on that because we don't have anything over here that gets us to the -6. We don't know what it looks like. They want you to find the value from a -6 to this -2. Show the work that leads to your answer. What that would mean is either up here on the graph or down here where you have some space, you need to make sure you are showing the work that would have gotten you that. So if we kind of look at this, what we know is from a -6 all the way over here to 5 is a value of 7. What we want to figure out is what was our value in here. So what we really just want to do is take that overall value of 7 and subtract away the value that we can calculate. And then that would be the value we can calculate would be from the -2 through the value of 5. That we can do based upon the graph at the top of our paper. So that would give us 7 minus, and then if you recall, the way we integrate a function is finding the area enclosed by that function in our graph. So we would have to then begin that process. So let me try to write this small where we can see this. So this would have an area here, this triangle of 1/2. We would have a triangle value here of this whole thing now from a -1 to what we would know here has to be a 0.5 based upon that slope. This would have an area of 3/4 because it's underneath the x-axis, it's going to be negative. We can then come up here to this bigger triangle. Let's figure out what that area is. It would have a base of 1.5. The height of that triangle would be 3. And for the area of a triangle, we would want 1/2 of that. All right, so, oh man. This was non-calculator also. I don't quite show that at the top of the paper, but this is non-calculator, so it's something we would want to be able to handle. What would that give us here? 3 times 1.5 is 4.5. So this would give us 4.5. 1/2 of 4.5 is what? 2 1/4. So 2.25. So that's what we would get right here. And then this, they give us this circle here. So this is another pain in the butt. Is the circle area we could figure out, at least this quarter circle, but that's not the area we want. Like we could figure out what that quarter circle is. We want the area here. So in order for us to figure out that area, what we would have to do is take the area of the rectangle. I'll show you what rectangle I'm referring to in a minute. And we would have to subtract the area of that quarter circle. So the rectangle would be from here to here to here. So we have a base of 3 and a height of 3. I guess that's actually a square. Same difference, I guess. What we're doing in Math 1 right now, if you are curious. So that area of the rectangle is 9. We would need to subtract away the area of that quarter circle. So 1/4. And then pi, we have a radius here of what? 3 squared. So that area is then 9 minus 9 pi over 4. All right. Goodness. All right, so then from there, let's go back to where we're going to be doing this. We have the overall value of 7. We're now going to subtract this area that we have accumulated here. So we would have 1/2 that was positive. We would have that negative 3/4 underneath the x-axis. Then we're back to a positive 2.25. And then we just found the weird area there. That was a 9 minus 9 pi over a 4. So 7 minus, and then this would give us what? A negative 1/4 plus 2 and a 4 would just be 2. So I think we get 11 minus 9 pi over 4. There's a negative in front of all of that, so we would get a negative 4 plus 9 pi over 4. Oh man, that was some tricky business there. All right, so letter B. There's a review. If you've been going through those review packets that I've been putting on here, one of the things that I talked about is on there quite a few times in one of the review packets. When we want to evaluate a definite integral and we know part of it, so like we know 4, but we don't know what this is, then we probably want to split up our integral. So that's what I'm going to do here. I'm going to try to do this below where we're going to have some room. So here's B. I'm going to split this integral. I'm going to go from 3 to 5 with 2 times f prime of x and then dx. And then I'm going to do plus 3 to 5 with 4 dx. This one's actually super simple. This was a very, very first type of integral that we ever evaluated, where we just said you're going to do 4 times the difference in x. Our limits show us our difference in x is 2. So we know that has a value of 8. Where this one, we want f prime, or at least we're dealing with f prime. All you're given to work with was this graph of f. So in this one, we're going to want to follow through with our antiderivative. So the 2 would stay. The antiderivative of f prime would be f of x from 3 to 5. We then know we've got to plug in the upper limit. So f of 5 minus our lower limit, f of 3. And then we hopefully can use that graph to figure out what these values are. So f of 5, if we come over here, look up at your graph, here's where 5 is at. Our functional value on the graph of f at that point was 0. Minus f of 3, if we just look at the graph, that's a problem because it's a decimal. It doesn't cross through a nice integer value. But, oops, that's why they gave you this point right here. When f is 3, or x is 3, we get a functional value of 3 minus root 5. Man, they like these, don't they? So then, what do we get? 2 times negative 3 plus root 5. Honestly, I believe they will just take this if you left it. Like at this point, I'm about ready to leave it. But then we can go ahead and distribute. If you wanted negative 6 plus 8 would be a 2. And then plus that, let's see, I already messed up, 2 times the root 5. See? Hopefully I've left enough room here. You're given a function g now. G is the integration of that graph of f, another absolute maximum value of our function question on a closed interval. So very, very similar to the one that we have just done. So for letter C, we're going to want to list candidates. 2 candidates for certain are going to be a -2 and 5 because those are our endpoints. We can also get candidates, since I want the maximum of G, it would be where G primed is either 0 or undefined. All right, so take the derivative of that function. So G primed would equal, another little rule from the previous question as well, the derivative of the integral would cancel, the x gets substituted in, G prime is equal to f of x. F of x just so happens to be the graph at the top of the paper. We want to know, where does this equal 0? So if we come up here, it would have equaled 0 at -1, and it would have equaled 0 at 1/2. So those are our other candidates. So we want to do G of -1, G of 1/2. All right. From there now, we just need to figure out what these values are. The first couple are pretty simple. G of -2. If we are plugging it into this function to figure out our values of G, you would let your x be a -2. Well, when we do that in the integral, both your lower limit and your upper limit are going to be a -2. If I can try to squeeze that in here, that upper limit becomes a -2, and we know if our limits are the same, we're always going to get a value of 0. G of 5 is pretty simple. We've already found it, because that would, if we evaluated that, we would plug in that 5 into your upper limit. And we've already found that right here. If you can see where I'm underlining, that was this mess that we got over here. So this right here was the value of G of 5, and that was 11 minus 9 pi over 4. Notice we're looking for a maximum. You would not have had a calculator in your hand, so you would definitely want to kind of understand what is 11 minus 9 pi over 4. 9 times pi is about 36. It would obviously be a little bigger than 36, but 36 is a nice number. 36 divided by 4 would be 9-ish. 11 minus 9 is a +2 or so. So right now, ballparking G of 5 as a +2. We still need to figure out G of -1. Really found that also. If we're going to be going from a -2 to a -1 in our integral, we've already found that. So here was the G of -2 to the G of a -1. It found that the amount of change underneath that graph of f from a -2 to a -1 was a half. So again, right now we're ballparking this guy here as about a 2. So definitely bigger than the 0, definitely bigger than our 1/2. G of 1/2 would tell us that we're going to go from the -2 to a +1/2. We've already done that work. We would have had a +1/2 here, but then we would have subtracted 3/4. So a +1/2 minus 3/4 gets us to this 1/2. That would be a -1/4. That is your justification. Notice they use the word justify. Don't explain this. Don't try to put it into words. List your candidates. Show them what all 4 of the values are. And then now very clearly, this is the one that's the largest. Anticipate some ugly math like this. Since they've gone to the 4 no calculator questions, they really make them do some ugly stuff. So don't be surprised. Don't be frustrated. And don't think that you won't have to be doing this in a couple of weeks. Yours are all supposedly non-calculator, although with the calculator, I guess, in your hand, since they can't monitor that, might make that a little bit easier. All right, next question. It says a cylindrical barrel with a diameter of 2 feet, so you'll see that at the top, 2 feet diameter, contains collected rainwater as shown in the figure above. The water drains out through a valve that's not shown at the bottom of the barrel. The rate of change of the height of the water in the barrel with respect to time is given by, so dH dt is the rate of change in the height of our water. H is going to be measured in feet. Time is going to be measured in seconds. They gave you these. I gave you these back in the day. They would expect you to know basic like circles, squares, but anything with cylinder, sphere, cones, whatever, they'll give you those. A, find the rate of change of the volume of the water in the barrel with respect to time when the height of the water is 4 feet, indicates your units of measure. So they almost always ask for your units when we're doing these related rate problems. So the rate of change in the volume, here is the volume of our water. So I don't think I can squeeze all that in. So we'll do that down here. So our volume for a cylinder, 4 pi r squared h. What we are trying to figure out is, what are we trying to figure out? The rate of change in our volume. So this is telling us we want to find dV dt. So we talked about how the only way we can take the derivative or get the dV dt, all these rates of change, is by taking the derivative. So there were a couple of ways we could do this. Let me show both, just in case we have forgotten. These are the ones where you're going to take your derivative with respect to time. So the derivative of v here would be dV dt. This would be a product rule between pi r squared and h. Derivative of the first term would be 2 pi r and then dr dt. Leave your h. Plus pi r squared, and then the derivative of h is dh dt. We're looking for dV dt, so we should be able to come up with the rest of this. The radius we could identify. You were told at the top here the diameter is 2 for that cylinder. So that would mean the radius throughout that cylinder would be a 1. We don't know the rate of change of our radius yet. We don't know the height of our water yet. We come over here though, and we would do our radius as a 1 squared, and then dH dt you were given, it's up here, is a negative 1/10 times the square root of our height. Our height you were given here, we're going to be doing this when our height is 4. So I guess over here we do know our height. We're going to do this when our height was 4. When we did this, I gave you one of these as a partner assignment. A lot of us were questioning, well, where's dr dt? Like, we don't know what dr dt is right here. But then we went back to our cylinder. I would point you back here. If we understand what dr dt stands for, it's the rate of change in the radius with respect to time. And if you look at a cylinder like this, the radius doesn't change. So this dr dt has a value of 0, meaning all of this here just cancels. And then what we would be left with then is our answer dV dt. So this is really just a pi times a 1. And then you would have what, a negative 2/5. So that would be a negative 2/5 pi. Sorry, negative 2/10 pi, which would reduce down to a negative 1/5 pi. All right. Now the other way, if you remember, we could have done these. Let me bring this over so we have space. Is if you recognize one of the variables as a constant right away, the radius in a cylinder is always going to be a constant, then this becomes a much quicker and easier problem. You can just plug that in right away. We don't need to worry about its rate of change because it doesn't have one. So we can plug that constant in right away, take your derivative, and we would get dV dt would equal pi and then times dH dt, and then the same exact process. Plug in your dH dt, which you were given up here again at the top, negative 1/10 times root h. We now know our h is a 4. You'll get that negative 2/10 pi, which reduces down again to the negative 1/5 pi. All right. Okay, B. It says when the height of the water is 3 feet, so we're going to do, I don't know, I'm going to squeeze this in. So we'll try to squeeze in B here. So when the height of the water is 3, so we're going to do this when 3, is the rate of change of the height of the water increasing or decreasing? So again, it's not asking if the height of the water is increasing. So it doesn't just say, is the height of the water increasing or decreasing? It's asking you, is the rate of change of the height increasing or decreasing? So it's really kind of asking, is your derivative increasing or decreasing? All right. So our derivative we were given, so here's dH dt would equal the negative 1/10 root h. We want to know, is that increasing or decreasing? Like we said earlier, we know if something is increasing or decreasing if that something's derivative is positive or negative. So we want to take the derivative of this and then determine if it's positive or negative at this time. So if we take our derivative, this would now be our second derivative. So we throw some exponents in here. This has a power of a half. So we do our power rule with this half power. So a negative 1/10 times a negative 1/2 would be what? A negative 1/20th h to the negative 1/2, and then times dh over dt. We now go ahead and plug these the value of h of 3 in. So you're going to get a negative 1 over 20. This is really 1 over the square root of h. H is 3. Multiplied by dh over dt, evaluated at the time of 3. And then dh dt would be, I'm getting this from the top, the negative 1/10 times a root h again, and we now know h is a 3. So the root 3's would cancel. And what we should end up with then, if I have just enough space here, is 1 over 200. Since that is greater than 0, that would tell us that the rate of change in our height is increasing because h double primed is greater than 0. Okay. I have no idea how I'm going to fit this letter C in. It's the main reason I wanted you to see this question, because this is our best. Let me figure out if I can try to erase this. I'll pause you. All right. I just deleted the whole darn thing. C's the big one. Separable differential equations, very, very common. And sometimes people get lost in this. These kind of get thrown in like in a part C. This is probably worth 4 or 5 points. I'll kind of walk you through how these points are counted. So it says at the time of 0 seconds, the height of the water is 5. So they're giving you an initial position. It says using separation of variables, find an expression for h. Well, all we were given to work with, we were given the graph. That doesn't do us any good here. What we were given is the derivative of h. So if you think about what that means, we were given dh dt to equal a negative 1/10 times a root h. So separation of variables, this goes back, understand though first, if we're looking for the actual height in terms of time, and this is our derivative, we've got to do the antiderivative of this. What we had to do though when we did these is, remember how we would multiply the dx over? In this case it's a dt. We would still need to do that. And then this root h we would have to divide over. So that ultimately it looks like this, dh over a root h, and then that would equal a negative 1/10 times dt. From there we would do our antiderivative. So by separating those variables, that's almost always just 1 point. So when you do these differential equations on the AP test, separating those variables gives you 1 point. We then want to do the antiderivatives. The antiderivative is a negative 1/10 t plus our constant. Over here, understand this is really a 1 over a root h on the left side, which is really an h to the negative 1/2. So that's how we're going to do this antiderivative on the left. So we'd add 1 to that power, so you'll get h to the positive 1/2. If I divide by 1/2, that is a 2. Okay. We now talked, when we did these, we can either solve for C first, or we can solve for H first. I'm going to solve for C. That's what most people did. We can do that with this information up here. We know that if we let our height be 5, and our time be 0, so that just means this expression cancels, we can then get our C. So we would then have 2 root h would equal a negative 1/10 t plus 2 root 5. Our goal is to solve for h, so the next thing we would do is divide everything by 2. So now root h would equal a negative 1 over 20 t plus the 2, when I divide into that 2 root 5, would just leave us with a root 5. We then need to square everything. So if I square this side, square that side, do not try to simplify this. Our height at any time is just the negative 1/20th t plus your root 5, that quantity squared. Big points here. All right, these are usually 4 to 5 points with the differential equations. It's another one that I just can't see us taking a test where that's not going to be a part of it. I'll definitely give you, over the next couple of days, another question that deals with that. Okay, last one. Another thing that, if you had 6 questions, I would tell you, without a doubt, you would probably get one that has a table involved. So number 4, the height of a tree at time t is given by a twice differentiable function h. H of t is measured in meters, and t is measured in years. Selected values of h are shown above. So it says, using the data, estimate h primed of 6. Using correct units, interpret what this means in the context of this problem. So they want us to take the derivative of the function h. We don't have the function h, we just have a bunch of data points in a table. So we definitely have done this. The way we approximate a derivative, no way you don't get tested on this. The way we approximate a derivative is with the average rate of change. So we want to do an average rate of change. We have to have an interval in order to do that. So we've talked about how if I want to do it at 6, the 2 closest values are here. All right, the 5 and the 7. So we would want to do h of 7 minus h of 5. Let me adjust here so that's somewhat legible. And then all divided by 7 minus 5. Look at your table. We would have 11 minus 6 over 2. So that is what, 5 halves. Think about your units when you write this. So it says using correct units. Write down what we just found in this problem by doing the average rate of change. This would give you a unit. The 11 and the 6 had a unit of meters. The denominator had units of years. So what this is telling us then in terms of the height of the tree is the tree, what's going on here? Yeah, the tree's height is increasing at a rate of 2.5 meters per year at t equals 6 years. Okay. All right, B, explain why there must be at least one value from 2 to 10 such that h primed of t is equal to 2. So this was the very first review that we did. Typically it gets asked with a table, and what we talked about back in that day. If you are given an interval and you start talking about explain why there must be something that's true or maybe something false, typically, if we kind of then come up here, you were told that this is twice differentiable. What that then also means is we are also continuous. So when we start combining the ideas that we're continuous and differentiable and start asking about what has to be true, almost always what that's getting at is the mean value theorem. And the mean value theorem guarantees that on a particular interval, if we have a function that's continuous and differentiable, the average rate of change would have to equal your instantaneous rate of change. Okay. Now, this one's a little trickier because typically what that would mean is you would do h of 10 minus h of 2 over 10 minus 2 because that's the interval that you were given. But when we do that, you're not going to get a value of 2 for this. If we did 15 minus 1.5 and then divide that by 10 minus 2, you don't get a value of 2. We would get what, 13.5 minus, or divided by 8, whatever 13.5 divided by 8 is, we would also have that value for sure, but it doesn't show that we're going to get a value of 2. So what we would like to do, somewhere in between 2 and 10, is there another interval that would give us an average rate of change of 2. So instead of this, if you look at your table, think about if we did, again, let me make this a little bigger. Hopefully we can then see all of this still. if we did h of, what did we want? 5 minus h of 3 over 5 minus 3. Yeah. So we're using this guy and this guy. What we would get is 6 minus 2, all divided by 5 minus 3. And notice how you're going to get 4 over 2 here. Since our average rate of change between 5 and 3 has an average rate of 2, that guarantees that our instantaneous rate of change would equal 2. So when they ask you to do this question, and it's pretty common, you need to show the work. So set up the average rate of change problem. We've set it up, we show that value, and then pretty much, as long as you use the words mean value theorem, they will accept that as your justification, as your explanation. Okay. Typically, usually, in the ones that we did in the review, and again, this is just them being creative, when it doesn't look just like a problem that you've seen before, again, be confident, don't freak out. What are they doing? They're still testing us on the same stuff that we've done before. Typically, you just do 10 to 2. You do the average rate of change from 10 to 2, and that average rate of change is what they gave you. Here, they made you kind of find something within the interval and figure out where our average rate of change would be A2. And that, in this case, was from the interval of 7 and 5. Wait, did I put 3 here? Sorry. This should have been H of 7 minus... Holy cow. Sorry, the PDFs suck for me to write on. Here's what we used. Let me try this one more time. We would have done H of 7 minus H of 5. All divided by 7 minus 5. That's where I'm getting... No. I'm correct. Never mind. Forgive it. I just said that. We're good. Moving on to letter C. It says use a trapezoidal sum with 4 subintervals. So trapezoid rule, subintervals indicated by the data in the table to approximate the average height of the tree over the time interval of 2 through 10. Okay, letter C. If you need to see the previous ones, go back. I'm trying to create space here so this doesn't become too ridiculous. C is asking for the trapezoidal sum with 4 subintervals indicated by the data table to approximate an average height. So first, let's deal with our trapezoid rule. 4 subintervals indicated by the data in the table. What that almost always means is we don't have a common change in time or common change in x. So if we go to our table, here our change in time is 1, here it's 2, here it's 2, here it's 3. Since they're different, we have to set up trapezoid rules for all of them. So as we go through this, you're going to have your 1/2 for the trapezoid, always. The first height is the 1, the change in x, and then we would use the 1.5 plus 2. Second one, you're going to have 1/2. Your change in time is your height. That's going to be a 2. And we're using the values of 2 and 6. The third one is 1/2. Change in time is 2 for the height, and now we are adding 6 and 11. Our height for the third one, or fourth one, is 3. Those bases are 11 and 15. All right, but think about what your units are right now. We ultimately want an average height. So our height better be getting measured in meters. So we're doing the trapezoid rule, but if you think about what your height is, what your units are going to be right now, the 1.5 plus 2, the 2 and the 6, the 6 and the 11 and the 15, those all have units of meters. The 1, the 2, and the 3 here all have units of years. So the unit attached to this value right now would have a unit that's odd. It's meters multiplied by years. What we want is a unit of meters. If we pick up on the idea that we want an average height, that couple of things, paying attention to our units, no, we want to get rid of years. So what that would tell us is not only are we doing the trapezoid rule, We also want to multiply by the number of years that we have covered. And since it was 2 to 10, we would multiply that by the 1 over 10 minus 2. What this question really is an average value problem. It's a 1 over a b minus a, integrating from a to b, f of x dx. When we do the trapezoid part, the trapezoid is approximating that part of the problem. That's what we just set up here. But then the average part is us having to multiply by that 1 over 10 minus 2 out in front. All right, now this would have been a non-calculator question. So again, don't think they won't do this to you. This is non-calculator. This is from 2 years ago, the table question from 2 years ago. You would then have to be able to navigate through this, being very careful not to make some sort of a mistake. All right, I'm going to cheat. I'm going to plug it into my calculator, so give me a second. And even doing that, here's what I'm guessing you would want to do. Just do 1/8 and then multiply that by whatever you're going to get here, because it's going to be kind of an ugly decimal. You'd get here 65.75. And I just don't see them expecting you to have to do that. I think you could probably leave this step right here, especially if you're crushed for time. I believe you can just leave that, and that's an acceptable form for that answer, especially when it's weird like that and pretty messy. Okay, and finally the last question here. It's another related rate question. The height of a tree is given by this function g, where x is your diameter of the base of the tree in meters. When the tree is 50 meters tall, the diameter at the base of the tree is increasing at a rate of 0.03 meters per year. Remember, x is the diameter at the base of the tree. So when the diameter of the base of the tree is increasing at that, what that really gives us is dx dt is equal to 0.03. So it says, according to this model, this equation, what is the rate of change? Rate of change implying derivative. So what is the rate of change of the height of the tree with respect to time? So that means it's a related rate question. We're going to do everything with respect to time in meters per year at the time when the tree is 50 meters tall. So if we took that function, g of x is equal to 100x over 1 plus x. Little test of your quotient rule, where it's going to be your bottom multiplied by the derivative of the top minus the top, the derivative of the bottom, all over your denominator squared, and then times the derivative of your x, since that's what we just took the derivative of, which is your dx dt. And clean this up a little bit if we'd like. Some good stuff is going to happen here. If we distributed, you get 100 plus 100x, but then you would subtract the 100x, all divided by 1 plus x squared. So the 100x's are going to cancel, times your dx dt. And then now, move this up just a bit, we're trying to figure out what happens at an x value of, a little careful here, the x value is going to be 1 because they ask you at the time when the tree is equal to 50. Notice how you're not plugging into t here, you're plugging into x. So back up to the top here. You'd have to figure out in terms of where did the 1 come from. Here's your height, because again, they gave you your height is 50. So if we come down here, g of x is our height, and it equals 100x over 1 plus x. You're told you're going to do this when our height is 50. Solve this, so I'm going to multiply this over to get 50 plus 50x equals 100x. Continue to solve this equation, and what we find is the x value is your 1. So that's what we're plugging in over here. So we would get 100 over 1 plus 1 squared, and then the dx dt value that we know is happening at 50 meters tall, which is when we're evaluating it here in our answer, is the 0.03. All right. So that is what, 425 times 0.03. And again, this probably is okay. I would think this is probably okay. You'll have your calculator in your hand. I don't know why I'm worried about you not having your calculator. You can just multiply these together, and that should give us 0.75. Okay. All of these are pretty common. Don't think if you're sitting there now saying you can't do these, you wouldn't be able to get through all of these by yourself. It's very, very, very rare that people get all of every one of these free response questions. Some are more fair than others. Some are harder than others. Don't get lost in that. The average score on these free response questions are all 9 points. Average scores anywhere from, a high 3 to a low to mid 6. There are very few people who are knocking all of these out and getting them 100% correct. Okay, so do your best. Again, I'll throw down a few more of these types on Tuesday of next week, so you can continue to see them. The more you're exposed to them, hopefully, the easier they are, and you learn not to get too worked up or freak out when you see something that you don't know how to do initially. All right, with that, have a good weekend. We'll talk to you guys next week.